Hey everybody, in this video what we're going to look at is limits, but this time we're going to look at limits as x approaches infinity or as x approaches negative infinity. In the previous lessons we were simply looking at it as x approaches a certain value. Okay, what we're going to find here is x approaches positive or negative infinity. So again, I'm just going to I don't know. What am I going to look at here? Let's go for some crazy looking graph like this. Hey, a cubic. Okay, so I'm going to say as x approaches infinity, so as x continually gets really, really big, what are the y values approaching? And as x goes to negative infinity, as x gets really, really, really small, what are the y values approaching? So that's what we're looking at this time. So not on the interior of our graph, but maybe on the exterior of our graph, right? Okay, let's try this. Let's examine the limits as x goes to infinity for these next couple. Okay, the limit as x goes to infinity of 3x cubed. Well, if you remember back to the last couple of lessons, I said always try direct substitution. Well, I can't really directly substitute infinity, like it's not a number. But I mean, intuitively, we can kind of think about it. Infinity cubed is infinity, and infinity times 3 is infinity, right? Like, the limit doesn't exist. But again, I want you to write positive infinity for a sense of direction as to what this is doing. Because if we're thinking about what this function here looks like, it actually looks a lot like the one that I just drew a second ago. Here's what this function looks like. 3x cubed. There's the function 3x cubed. So as x gets really large, what are the y values doing? As x gets really large, the y values are growing without bound. They're continually getting larger. So the limit doesn't exist because the limit has to approach a real number. Why we'll see positive infinity written is simply for that sense of direction for when we go to draw these things. Okay, let's try another one. The limit as x goes to infinity of 3x over 7x plus 4. Okay, well, let's try this little piece of substituting in infinity, right? Like, what happens here? I get 3 times infinity over 7 times infinity plus 4. What the heck does that equal? I don't know. We can't really do this. We can't say infinity divided by infinity. That's known as indeterminate. Indeterminate. Don't ever call me on my spelling, but that's how you spell it, indeterminate. Can't do it. You can't tell me what infinity divided by infinity is. It's not 1 because it's not a real number. So what are we going to do? Well, we're going to do something really, really smart. What we're going to do is we're going to divide by the highest power that I see in my denominator. Why would I do such a thing? Watch what's going to happen. I'm going to divide everything by x. So 3x divided by x. 7x divided by x. 4 divided by x. I'm allowed to do this because I'm changing how it looks, not what it's equal to, right? Okay, let's simplify. Limit as x approaches infinity of 3 over 7 plus 4x then. Okay, weird. Why did he do that? Well, now, my friends, what happens right here? As x goes to infinity, 4 divided by infinity, 4 divided by a really large positive number, right? A really large positive number. Well, anything divided by a really, 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 really large number is going to be 0. That will go to 0. I'll say that again. Anything divided by a really, 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 really large number is going to be 0. So what have we got left? we've got the limit as x goes to infinity of simply 3 over 7 plus 0. This is 3 over 7. So when we've got a rational function like this, what we will do is we will divide by the largest power in the denominator. Okay? And what we actually just found, if you think back to 30-1, my friends, we actually just found the horizontal asymptote of this graph, right? A horizontal asymptote is what happens as x goes to infinity. We'll talk about graphing later on in this course. Okay, let's try that again. So I look at this next one here, limit as x goes to infinity of 5x squared divided by 7x cubed plus x. Okay, I can't really substitute an infinity. It doesn't make sense. So what I'm going to do is I'm going to divide everything by the highest power in the denominator. So I'm going to divide everything by x cubed. Okay, takes me a little moment to write it all out, right? No big deal. X over x cubed. Make sure you're keeping the limit here, right? You need that. Can't get rid of that until you do some substitution. Okay, let's simplify. So the limit as x goes to infinity. I'm going to have 5 over x over 7 plus 1 over x squared. Okay, now what happens? Well, let's just look at this piece by piece. As x goes to infinity, 5 divided by a really, really, really big positive number will be 0. 7's just 7. There's no x in it. Plus 1 divided by x squared. 1 divided by a really, 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 really big number squared, that's positive, will be 0. Guess what I get? 0. That's what the limit is. The limit as x goes to infinity for this function will be 0. All right, let's try another one. The limit as x goes to infinity of 9x squared, 1 minus x. Okay, again, what I'm going to do is I'm going to divide by the highest power in my denominator. So I'm going to divide everything in this case by x. Okay, so the limit as x goes to infinity, and what I'm going to get now, I'm going to get 9x squared divided by x, all divided by 1 over x minus x over x, is the limit as x goes to infinity of 9x over 1 over x minus 1. Okay, what happens here? So now when I try to sub this in, what am I going to get? Well, in the numerator, I'm going to get 9 times infinity, okay? And in the denominator, I'm going to get 0 minus 1. Well, what I've really got here, friends, is I've got infinity divided by -1. What the heck is that? Well, really, if I want to think of that, that's negative infinity. The limit of this thing actually does not exist, right? The limit of this thing does not exist because the top, if you want to think of the numerator, the top has a degree of 2, and the bottom has a degree of 1. So what that tells me is the top is growing faster than the bottom. The numerator is growing faster than the bottom. So as this thing's growing, the top is going to go off faster than the bottom. We're not going to have a limit. So in this case, what we're going to say again is the limit does not exist. And remember, the fancy way to write that in math is that backwards E with a slash in it. Okay? So really what we just analyzed, friends, was 3 different cases. On this one here, we had the numerator and the denominator had the same degree. Do you see that? They both had a degree of 1. In the next one, we had the denominator, there's that thing again in my way, the denominator is growing faster than the numerator, and we had an easy answer of 0. And in this one, when the top is got a bigger degree than the bottom, and the numerator has a bigger degree than the denominator, we will not have a limit because the top is going to grow without bound in comparison to the bottom. Okay, so three different ways to analyze a rational function. Okay, so that's not too bad. So we're dividing by the highest power in the denominator. All right, there's one last one that we want to take a look at. Okay, what we want to talk about here before we get to our last example is what about the square root of x squared? It's a bit of a funny thing. Okay, the square root of x squared. Well, what is this thing really equal to? Well, I'm just going to sub in a number for a second. So what if I subbed in, I don't know, I'm going to say -1. Well, -1 squared is 1, right? So now I've got the square root of 1, and we all know the square root of 1 is 1. But what if I did this? Still sub in -1, but now instead of squaring the function first, I do this. I simplify it first, and I say the square root and the square are inverses, so they undo each other. Well, if they undo each other, then I'm simply left with -1. So what the heck is going on here? I get two different answers. I get 1 and -1. So the square root of x squared is not x. The square root of x squared is actually the absolute value of x. And if you remember back to 20-1, what this tells us is an absolute value has a positive and a negative portion. A positive and a negative portion. And the positive portion is when x is greater than or equal to 0. And the negative portion is when x is less than 0. Okay, so this is going to be really, really, really important, okay, in a couple of tricky examples that we'll see as we go through calculus. Okay, let's look at one of those tricky examples right now. Take a second to look at these two. The limit as x approaches infinity of root x squared minus 9 over x, and the limit as x approaches negative infinity of root x squared minus 9 over x. How are we going to attack these two things? Okay, so why were we talking about this little idea? Well, look at this one here. When we've got this square root of x squared there in the numerator, something's happening. So let's try this. I'm going to divide by the highest power in the denominator. Okay. It's worked so far. Let's see if it keeps working. So I divide the numerator by x, and I did not divide the denominator by x. Perfect. Look what happens in the denominator. X divided by x is 1. So I'm left with this. But look at, aren't I just right back almost in the exact same place where I started? So dividing by that highest power of x didn't really do a heck of a lot for us, right? We're just kind of went in circle. So what we're going to do to kind of get out of that circle is we're going to factor out a square root of x squared out of that numerator. Because the square root of x squared is, you got it, x, but it's x as long as x is going to infinity, because x is greater than 0. What do we have left inside our radical? Right there. So now, this is positive because x is greater than 0. We're going to positive infinity. So now, this will be x. Those two things will divide. And now we can do direct substitution. Well, the limit as x approaches infinity of the square root of 1 minus 9 over x squared. Well, 9 over x squared as x goes to infinity is going to go to 0. So we've really got the square root of 1 minus 0. And guess what? That's just 1. Okay, let's try that again. Let's try it on the other side as x goes to negative infinity. Let's go pretty pro. Okay, same idea. If I try to divide by x in the denominator, you can see we're just going to end up in the same spot, right? So what we'll do this time, this is a bit of a special case, right? Is we'll factor out root x squared, just like that, out of our radicand. We're left with 1 minus 9 over x squared over x. But here's the big difference here. The square root of x squared as we go to negative infinity is negative. The reason why it's negative is because of this important definition right here. The square root of x squared is equal to negative infinity as x is less than 0. So let's now see what we end up with. How is it different this time? Well, now these two will divide out, but now I'm going to write this down. The limit as x goes to negative infinity, that's now negative 1. 1 minus 9x squared. When we substitute this in, 9 divided by negative infinity squared will go to 0. We now have negative 1 times root 1, which guess what is negative 1. So these two limits actually go to different values. Now, what does this look like? One of the things that we could do all along that we haven't been doing is graphing these things. This is the graph of that function, root x squared minus 9 over x. And I'm even going to zoom in just a little bit. I'm going to change my window settings to be, let's go negative 3 to 3. There is that function. So you can see on the right-hand side here, as x goes to positive infinity, the y values are approaching 1. And as x goes to negative infinity, this direction, the y values are approaching negative 1. So that's a sneaky little trick that I want you to remember. It's a very unique case, but I would very much like it if you remembered that when we're here and we see that root x squared, I need you to remember this rule. Okay, friends, little tricky way to end the lesson, but there it is. See ya next time.